Hello. Pre-calc, this is after Thursday's class, and you have a little extra time tonight, but I know you're tired. But let's go ahead and do three measly problems. We're trying to keep these principles in mind for Tuesday's test, and the more we do, the better. This will probably conclude our review, so there's a 10 problem set, but I'm going to do 3 with you now and see how it goes. Alright, let's look at problem number 1. You don't have this worksheet yet, so I don't think you need to write the problem down, but maybe write the answer down so in your comp book, so you get credit for watching this, and then you can transfer the work and the answer to the sheet when you get it tomorrow. Beth and Shayna each purchased 1 raffle ticket. If a total of 11 raffle tickets are sold and 2 winners will be selected, what is the probability that both Beth and Shayna win? Alright, so we can see that we do a probability of any event by looking at the number of ways the event can occur divided by number of ways possible. Alright, so we've been dealing with this magic fraction for a while now. So let's look at this case. So we have 11 raffle tickets. 2 are going to be drawn from the 11, so I kind of circle the important numbers. 2 are going to be drawn to be winners. So Beth and Shayna has each drawn bought one raffle ticket, and what's the probability that both are winners? Alright, so we're going to decide how to do this by counting, and what is the number of ways? So I'll put, there's 2 raffle tickets, say Beth's and Shayna's. How many ways is it possible for Beth, we'll say we'll put Beth here and Shayna here, how many ways is it possible for the first girl to buy a winning raffle ticket? There are 2 ways because there are 2 winning raffle tickets. But once she buys one of them, how many ways are left for Shayna to buy a winning ticket? There's just 1 way left. And on the bottom, there's no restriction. So how many ways could we buy any ticket? Well, there's 11 different tickets, so we could buy any of those. And once one is bought, there's 10 ways to fill in the next ticket. So ticket holding spot. So we get 2 over 110. Let's reduce. So that's 1 out of 55. The chances are 1 out of 55 that both of them will buy a winning ticket. Alright, let's see how you do on this one. A meeting takes place between a diplomat and 14 government officials. However, 4 of the officials are actually spies. If the diplomat gives secret information to 10 of the attendees at random, what's the probability that no secret information was given to the spies? So, I want the probability that no spies received this secret information. Alright, so again, we've got our magic fraction. I often like to do the denominator first. I should have done that on number 1. I hope that you could follow well. Alright, so there are, he's going to give information to 10. So the government guy is going to give information to 10. Alright, so how many ways can he give information to the first guy? And there's no restrictions on that. Well, how many different ways can information be given? Well, I calculated that there are 14 different government officials. Okay, so we're doing the probability that no spy receives secret information. So how many different ways can a person fill this spot? Well, there's another 14 different government officials. So we don't care if they're spies or not. In the denominator, there's 14 different officials. Some of them might be spies, we don't care. So once that one's chosen, 13, 12, 11, 10, 9, 8, 7, 6, and 5. So that's how many different officials could take those spots, those 10 spots. So now on the numerator, that's where we get a little pickier. Here we didn't care what official was receiving information. Up top, we want to demand that these people are not spies. So, how many ways could I fill the first spot with a non-spy? So you can see that how many were spies? 4. How many total? 14. So how many non-spies were there? 4 from 14 is 10. So there are 10 non-spies. So there's 10 ways to fill that slot with a non-spy. And once we do that, then we go in this fraction. Alright, so when I multiplied 10 times 9 times 1, divided by 14 times 13 times 12 to 5. So when I divided that large number on the top by the even larger number on the bottom, I got 1 out of 1001, which is the same as the fraction 0.000999. Alright. And this will be the last one. A fair coin is flipped 10 times. What's the probability of the coin landing heads up exactly 6 of the times? Alright. So on this one, we are expecting 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we're looking for exactly 6. 6 that are heads, so that means the last 4 will be tails, and it's divided by 2, 3. Alright, let's look at the bottom first, and we don't have any restrictions on the bottom, so this is a probability that heads 6. So we'll say 6 heads. Alright, so on the bottom there's no restriction like this, so there's how many ways could the first coin turn out? 2. It could be heads or tails. How many ways could the second coin flip turn out? 2. 2, 2, 2, 2, 2, 2, 2, 2. So that whole bottom is 2 to the 10th. Was it 10 flips? Which is 2 to the 10th And 2 to the 10th is something. Let's see what 2 to the 10th is. Two raised to the 10th is 1024. Now, on the top, how many ways could we fill this if it has to be a head on the first flip? How many ways could this be filled if it has to be a head? Has to be a head. How many ways can it be a head? All right, now we go across the line, and now we want to fill the rest of them with tails. So how many ways can a flip of a coin turn out to be tails? All right. However, this is one arrangement. So this was, and we've had this kind of thinking in some other problems, that was heads, 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 and tail, 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 tail. So that is one possibility where we would get 6 heads exactly. Or, there's that word that means plus, we could have tails, tails, and then 6 heads. And then 2 more tails. So we could have that arrangement as well. So notice if we were doing a count, or doing, the count on these, we would still have a 1, 1, 1, 1, 1, 1, 1, but that word or means we're adding this possibility to this possibility. So, and then how many more do we have? How many different combinations are we going to have when we have these 10 items and these 4 tails? Or we can say 6 heads. Actually, you'll see they're the same number. So either one, but since we're dealing with, the problem actually mentioned there'd be 6 heads. How many combinations of 10 items, taking 6 at a time? So that's how many of these, if I were going to write them all out, and they're all going to have the count of 1, but the or means I'll be this or this or this. I have to add those up. So I do this number times this number, which comes out to be 1. So what's 10 factorial over 10 minus 6, 4 factorial, 6 factorial? When you work that all out, I came up with 210. So this is 210 times all these ones equals 210. So 210 out of 1024, and that comes out to be 210 over 1024 equals 0.20508 with some rounding there. And if you kept it in a decimal, it reduces to 105 over 512. All right. So this is the kind of thinking that we are going to experience on the rest of this worksheet. Okay, hopefully this probability stuff is starting to sink in. If not, there's still time, so carry on, carry on.